This is like video 37. They're becoming less professional by the second. We talked about what statistical induction is. Let me explain what it's not so that we can lead into a conversation about bias versus variance. This is what people think statistics is like. They give you a bunch of data and they're like, can you find the answer? And the statistician looks and looks and says, oh, there it is, right there. There's Waldo. And what the statistician found is unquestionably true. It's deductive reasoning. There's no question, and it's completely accurate because there he totally is. No, that's not the way it is. It's more like climbing a hill, and every time you get some data, you take one step up the hill, and your goal is to get right up here at the top of the hill where there's truth. But if we made this picture looking more realistic, like there's no actual top to the hill. You can get more and more and more data. It's not until you have infinity data that you actually have the answer. So our goal in statistics isn't to find the answer out to infinitely many decimal places. We chop this off at some point, make a plateau and say, okay, as long as we get this close to the answer, meaning somewhere on the plateau, we're going to say it's good enough. And then we gather more data and slowly get closer and closer until the answer is within some range. And there we say, this is close enough to the true answer. This is the result. It's important to recognize as you do statistics, you never get the correct answer. But as long as you can get close enough, you can still make good decisions, business, biology, whatever your major is into, to help the client move forward with their science. So as we climb this path, there might be more than one path. Here's a green path that goes straight up the hill as fast as it can. That's great, that's ideal. This path travels around the cone and slowly gets there, meaning it takes more data using this method to get close enough to the answer that the client's going to be happy. Now imagine this scenario. Here's a path that climbs up fairly quickly. It's certainly a lot faster than that path that was winding around and around the mountain to get up to the top. But the path doesn't actually go straight up. There's bias in the result, but the bias is only small amounts and we're still within the range the client wants to get to. Could a path that's biased actually be a good path? Because with a little bit of data, you're getting something close. And yeah, this is something people argue about a whole lot. Let me give you an example. Here's a whole bunch of data. It happens to have kind of a bell curve shape. We want to find the middle. Here's some options. We could take the average, which should be the one you thought of first, because obviously that's a good pick, and it has all sorts of good properties if you've taken classes to talk about it, but you could use the median. Why? Maybe the median is easier on the computer and we're talking about billions of data points. I don't know, but the median is also an option. Or what if you only stored the maximum number and the minimum number? You add those together, divide by 2. That does an estimate of the middle. How good is your answer? Well, let's look at the variances. For x bar, it's sigma squared over n, right? This is what we hammer in the intro class. Sigma over square root of n if you wanted standard deviation. The median is pretty close, except it's pi halves. So in other words, the variance of the median is going to be just a little bit bigger than x bar. Or if we were talking about climbing the mountain, it means you get a smaller range with the mean than you would with the median. So you get 100 data points, the mean is going to have a tighter confidence interval. Using the median, your confidence interval is going to be a little bit wider. This method isn't as fast at getting to the answer. It doesn't have as much information, giving it more power, more efficiency. Now, max plus minimum, that's like a 1 over log n, which is distinctly slower than n. So getting these variances small, with the variance of the max plus the min divided by 2, you're going to need a lot more data before your confidence interval finally shrinks as small as you're wanting it to be. So based off this, we could rank the different methods, 1, 2, 3. Would you use a subpar method? Maybe if there was some extreme need, like the way the database was designed, forced you to use median instead of x bar. Okay, understand that your results aren't going to be as accurate, or you're going to need more data to make up for it. The argument of whether you want something unbiased or something that's faster but a little bit biased, we'll get into that in a little bit. Are there other options? Sure, take a look at this estimator. What I'm going to do is take x bar, multiply it by 0, and add mu. Well, guess what? One data point, I instantly have mu. That's like a path that portals you straight up to the top right in the middle. Fantastic. Why don't we use that? Well, if you had mu, then why are you trying to estimate mu? This isn't a realistic scenario, but it goes to show that when we talk about the best estimator, we want to talk about certain rules, like it's unfair to actually use the parameter you're trying to estimate in the equation. And so the rules we often put on are called regularity conditions. That's where things have nice probability bounds, the way that we're used to. And honestly, it's the way that it usually is in real life scenarios. What is the best estimate? It's going to be the one that is unbiased and efficient, meaning it goes straight to the true value and it gets there as fast as it can, meaning that estimator will have a confidence interval smaller, tighter as any others. What if you couldn't get there? Well, let's try at least consistency. Consistency says, yes, there's bias, but asymptotically, that bias disappears. This means if you have low amounts of data, you might worry. High amounts of data, it's going to be okay. For efficiency, it can have asymptotic efficiency. It's not the fastest estimator, but asymptotically, it's going to be faster among those that have the regularity conditions, which is the conditions we were talking about earlier. What if we don't have that? Well, how about of all the estimators I can think of, this one has the least amount of bias and it gets there faster. Maybe someone later will invent another one that's even faster, but for now, this is the best one I can find. And of course, the next step is to say, here's an estimator that's unbiased, but not efficient. A different estimator that's very fast and efficient, but has some bias. Which one do you do? Well, people talk about this a lot. One common way is to take bias squared plus variance and try to minimize that value. This is often an issue with Bayesian versus frequentist, and we'll have another lesson that's going to delve into what that difference is. But a frequentist would commonly say, I want unbiasedness. Start there, and then we can talk about what's most efficient among the unbiased estimators. Whereas a Bayesian would say, well, hold on, I'm okay accepting a little bit of bias here since this gives me such a more efficient estimate. And not a bad response. Neither one is right. It really depends on what the client is after.